So many of the things that we learn in algebra go back to those properties that we learned a while back, the commutative, associative, etc. This one is no different. The multiplicative identity, if you recall, said that any number times 1 is equal to that number. So multiplying by 1 doesn't change anything. But the key is we can change what the number 1 looks like. So we're talking about fractions. The number 1 can be written also as 1 over 1. Okay? It can be written as 1 over 1. It can also be written as any fraction where the top number and the bottom number are the same. 2 over 2 is 2 divided by 2, which is 1. It's equal to 3 over 3. It's equal to 4 over 4. It's equal to 19 over 19. Why did I write 5? Let's change that. 4 over 4 equals 19 over 19. So all of these things are equivalent. This is a statement of equality. So we can say sort of algebraically that 1 is equal to any number k over itself. 1 is equal to k over k. So we're going to combine this with this. Any number times k over k is still equal to the number that we started with. That's a key piece of information. So let's just pick a fraction. And we're going to do that to it. Let's make up a fraction. Give me any two numbers you want. Okay, I heard 4/7, 4 over 7. So we're going to multiply that times some other fraction, k over k, but we're going to pick some numbers. Let's pick a number for k. How about 3? Okay, great. So 3 over 3. 4/7 times 3/3, remember this is just equal to the number 1, is equal to, now think about how we multiply fractions. We multiply straight across. So this would be equal to 12 over 21. So what we found now is that 4/7 is equal to 21 or 12 over 21. These are equivalent fractions. They mean the same thing. They're talking about the same amount of stuff because remember, it's the relationship between the top number and the bottom number that matters. It doesn't matter how big these numbers are. What matters is how big they are compared to each other. And this is called raising fractions to a higher term. And a lot of the times we want to look at a fraction using different numbers. We want to look at the same comparison, but with different numbers doing the comparison. So here's an example of a question that might be useful for. Which is bigger? Sometimes you want to know which number is bigger, right? You want to, there was a quiz. One teacher scored it out of this many points, another teacher scored out of this many points. And you want to know, did you do better than your friend? So let's say that one person scores 17 out of 25 on a quiz, and another person scores 3 out of 5. So the way the grading system was a little bit different. Those are both fractions, and the question is which is bigger of the two? I don't know. It's hard to tell. It's hard to tell just by looking at them. Because if we tried to draw a picture of 17 out of 25, imagine splitting this up into 25 little segments, right? 1, 2, 3, 4, 5, 6, right? We'd have to draw so many of these little segments, 25. I don't even know if that's right or not. 3/5, on the other hand, would be just 5. We could picture that a little bit better. So this method isn't really going to help us much. But what does help us if we can compare the denominators together. Well, not compare them, but have the same denominators. Because if things have the same denominators, it's the same number of equal slices. And then we can simply compare the numerators. Okay? I can't compare the numerators yet because they're out of different denominators. So what we can do is we can look at this number 3/5 and say, can I change it? Can I turn this 5 somehow into a 25? By multiplying it by something, right? Remember, I want to multiply it by k over k. I want to multiply 3/5 by some number on top and bottom. Well, if I multiply both of them by 5, right? Multiply 3/5 by 5/5, it still has the same value as 3/5. It just uses different numbers. 3 times 5 is 15 25ths. So 3/5 is really the same as 15 25ths. And now our two denominators are the same. And so I don't want to compare this. I want to compare this. What's bigger, 17 25ths or 15 25ths? I think we know it's 17 25ths. So getting common denominators allows us to compare fractions to see which is bigger. And often that's a helpful thing for us to do. Here's another one. Try this one. Pause the video. 63 out of 100 or 16 out of 25. Which is bigger? So as you stare at that, what you want to do is say, can I somehow get these two denominators to be the same? And I can by multiplying this one by 4. So if we take 16 25ths and we multiply it by 4/4, remember it's just multiplying it by 1, so we're not changing the value. What we get is 64 100ths. So, which is bigger? 63 100ths or 64 100ths, right? Now I'm comparing this to this. And what you'll see is 64 is bigger. So, of the original fractions, 16 25ths has a bigger value than 63 100ths. So that's, again, a way to get, to raise our fractions to a higher term so we can compare the fractions. Now that's not the only thing we would want to do this for. What we're going to be looking at shortly is adding and subtracting fractions. There's another reason you get common denominators. We'll talk about that more. Often problems might be shown in a shorter version, where it's just, here's a fraction 2/3, and I want to know what that fraction would be if it had the denominator of 21. So you're basically looking to see what number is going to go up there. And the way that you might want to think about that is, well, pause the video and see if you can figure it out first. But the way is, well, what did we do down here? What did we do on the bottom? How did we change 3 to 21? We multiplied it by 7. And so we need to do the same thing to the numerator. 2 times 7 is 14. So we would have 14 21ths. Again, 2/3 and 14 21ths are the same number, the same value. They're equivalent. Okay, they have the same, they talk about the same amount of stuff. Well, no lesson would be complete if we didn't do the same thing with variables, right? So I'm going to take that same fraction, say we have 2/3, but now when we change it, the new denominator is 21x. And we have to find out what number is going to go up here. So the same, pause the video, try it yourself. You think about it the same way. How did we go from this thing to this thing, right? How did we change 3 into 21x? Well, what does 21x mean? It means 21 times x. In fact, I'm going to show you another way to even think about it. And it all goes back to those prime factorizations. 21x means 3 times 7 times x, right? Those are all the building blocks of 21x. So if we started with 3, and now we have 3 times 7 times x, you'll notice that these two factors are new. These are the two factors that we multiplied by to get 21x. So we have to take the bottom times 7x, which gives us 21x, and the top times 7x, which gives us 14x. So 2/3 would also be the same as 14x over 21x. And again, what we're doing is we're raising our fraction to a higher term. Don't look at this and say, okay, it's time to reduce, because we always reduce. No, we're kind of doing the opposite of that. We are introducing common factors to the numerator and denominator. We're not trying to remove common factors. We're actually introducing new common factors. One more. Negative 4 over 5n equals what thing over 15nm? So pause the video and try it yourself. Again, we're looking at the bottom. How do I go from this into this? That's the question. It can be helpful to factor this thing. That's even going to be more helpful once we get down the line, way down into Math 40. But for now, I look at 15nm, and I think about it as 3 times 5 times n times m. If we started with 5 times n, and I see 5 times n right there, what are the new factors that were introduced? Well, there was a 3, and there was an m. So we have to multiply the top and the bottom by 3 and m. 5n times 3m equals 15nm. Do the same thing to the top. Negative 4 times 3m will be negative 12m, right? It's just all of these three things multiplied together. The number negative 4 times 3 times some other number m, which we don't know what it is. So we would say our fraction raised to a higher term is negative 12m over 15nm. And that is raising fractions to a higher term.